This is lecture 4 for Radiochemistry 702. This lecture is on orbitals and energetics. The lecture will discuss molecular symmetry, the relationship between bonding and structure, and then go over some theories that describe metal-ligand interactions. The goal of this lecture is to provide a fundamental understanding of chemistry dictating complexes, particularly radionuclide complexes. So, one of the primary factors of this lecture is that structure is based on bonding. So the interactions of electron orbitals, the Ds and the Fs, are going to dictate the coordination chemistry. And the reason the importance of the coordination chemistry is that it is going to be related to spectroscopic behavior and how one can identify different chemical forms of the actinides in solutions or solid phases based upon spectroscopic properties. One of the first things we'll talk about within this lecture is molecular symmetry. Primarily the evaluation of point groups. When we talk about coordination numbers, we'll show the relationship between coordination numbers and point groups. And these point groups are a description of symmetries present in molecules. And the symmetries can be along the axes, planes, an inversion symmetry around a center of the molecule, and rotational symmetry. The importance of these point groups is they can be used with group theory to determine spectroscopic properties. And here's a table showing some point groups, C, D, T, O, H, shapes of the molecules, and some examples. We'll go over this, however this should really be a review from any inorganic chemistry you've had. There's a relatively straightforward method that's described in the next few slides on determining the symmetry of a molecule. There's flowcharts that one can use, basically answering each question, going through, and then you should wind up with the point group for the given molecule. This is half of the flowchart. The other half is listed here. And this entire flowchart can be seen on this page. Now we can go through this page using an example of this molecule. This is a planar molecule, metal center or center. This is like boron BH3 or some boron compound. So what we'll do, we'll go through this and use this flowchart here to identify the point group. So first thing we do, we look at the molecule and we say, is it linear? Well, from inspection, this is not a linear molecule. So we select no. We go to the next step. Are there two or more CN axes where n is greater than 2? Well, if I were to take an axis right through the center of this molecule, I can rotate it 3 times, 1, 2, 3, around that axis. That's a 3n, right? A C3 axis. But there's no other ones here. I could do this twice. I can do this one twice and this one twice. And as we see here, this is designated as C3. So there's only one C3 where n is greater than 2. So we're going to have to say no for this one. So we follow the chain here, go up to this point. Now we have to say, is there a CN? And we've already demonstrated, yes, there is a CN. So we go down and we look at this section where we select the CN, so that's with the highest n. That'll be C3. Are there 3 C2 perpendicular to this? Well, there's 1, 2, 3. So you see each arm off the metal center is a C2. So the answer to this one is yes. We see that we have a C3 and we select yes. So this brings us to here. And what this is asking, if we saw in the previous flow sheet, do we have a horizontal plane? Well, if I look at this molecule and I look in the black box, that is a horizontal plane. This molecule sits in that horizontal plane. I'm going to answer yes. So this point group is a D3 because our N is 3H. And that's what we get for this molecule. It is a D3H point group. There's two other examples on this slide. One is for water, H2O, determining the point group. The answer is that it's a C2V symmetry. And if we see here, there's a C2 axis. There's two vertical mirror planes. If we were to go through the identification tree, we should get to C2V. And then for ammonia, the molecules here, there's one C3 axis here. There's three vertical mirror planes. There's no horizontal mirror plane. And as an exercise, you can use these figures to go through the identification tree and identify the point groups for these molecules. One of the main utilities of evaluating the point group is to assess the potential spectroscopic properties of the molecule under evaluation. Here's a group theory table for the C2V point group. This shows which orbitals will be affected. And here one can get an idea of which bonds, which orbitals would be IR active and IR inactive. This is more of an example, and a full explanation of the group theory is beyond the scope of this course. However, this should be reviewed for anyone who's taken inorganic chemistry. One relatively straightforward relationship between geometry and the molecule can be evaluated by the coordination number. We'll go over some coordination numbers and the potential geometries. Here's a table that's listed showing the different geometries. For a coordination number of 2, we can have either linear, as an example here, or bent geometry. And here are the point groups associated with those geometries. And from this, we could also get the group theory information. For a coordination number of 3, as an example here, we have 2 shown on this slide where we have a planar, D3H, shown here, and a pyramid type, C3V. For a coordination number of 4, a few different geometries can exist: tetrahedral and square planar. For a coordination number of 5, 2 examples are shown here. We will have trigonal bipyramid, where these chlorines here form the trigonal phase, and these chlorines are above and below the plane, forming the bipyramid. Then a square planar, where these chlorines form a square, and one chlorine sits above, forming the rest of the pyramid. Going to coordination number 6, which is a very common coordination number, the basic structure would be this octahedron, and the symmetry can be varied by either stretching or squishing the points on this octahedron. We can get a tetragonal octahedron, a rhombic, that's what's shown here, or a trigonal distortion, where basically we have rotation within the octahedron. But the fundamental shape is an octahedron, and the other geometries are variations on that shape. Actinides can take higher coordination numbers, and here are some examples of coordination number 7, 8, and 9. See, there's a few different for coordination 7. Example here is pentagonal bipyramid, so there's a pentagon with a pyramid above and below. This 8-coordinate structure here is cubic, and the 9 is a tricap trigonal prismatic type structure. More detail can be found here on the website listed on this slide. we'll start discussing metal-ligand interactions, and possibly the simplest model is just treating those interactions as acids and bases, where the ligand can act as a base and the metal acts as an acid. These can be divided into hard metal ion interactions with hard bases. We can divide these groups into hard and soft ligands. Ligand hardness decreases down a group, so fluorine is harder than chlorine. Hard metals have high positive charges, small radii, and tend to have closed or half-filled configurations. Soft metals, examples are lead, mercury, have low positive charges and relatively large ionic radii. The lanthanides and actinides are both hard metals. However, actinides tend to have more covalent characteristics because of the 5f electrons, so they tend to be softer than lanthanides. So ligands with soft groups can be used for actinide-lanthanide separations by preferentially binding with the actinides. Here are some examples of hard metals and ligands, intermediates, and soft. As we see from the hard, we tend to have smaller ions, higher oxidation states, and the soft are larger and lower oxidation states. Another route for describing metal-ligand interaction is chelation. Chelation is where you have a ligand with more than one complexing functional group. An example would be ethylene diamine tetraacetic acid, EDTA listed here, and the coordination as shown here with copper. When you get this chelation and enhanced stability, it's due to the fact that you have coordination that's also driven by the geometry of the metal-ligand interaction. Fundamentally, these ligands can bind the metal ion either multiple times, either bidentate or tridentate. They can wrap around the metal ion, forming a stronger complex. Another route to describe metal bonding is with effective atomic number. This fundamentally describes the number of electrons surrounding the metal ion that's involved in bonding. For instance, transition metals can have 9 possible bonds, 5d, 3p, 1s, 18 electrons can be involved in those bonds. So it's possible to have an effective atomic number of 18. In fact, metal ions can have effective atomic numbers as high as 20 and as low as 9. Some certain geometries, such as square planar with 8d electrons, has a 16 electron effective atomic number. And as shown in this table here, certain complexes, such as these nickel complexes here, can have effective atomic numbers greater than 18. We can expand our models to describe metal-ligand interactions through some enhanced theories, and these theories we're going to discuss in the upcoming pages. The first theory we'll introduce is the molecular orbital theory. In molecular orbital theory, the orbitals which compose molecules are from overlap of atomic orbitals. The number of molecular orbitals equals the number of combined atomic orbitals. There are different types of molecular orbitals that can be formed through this route. Bonding orbitals, which are lower in energy than the atomic orbitals. Non-bonding orbitals, which have the same energy and property as the atomic orbitals that are the non-bonding orbitals. And anti-bonding orbitals, which are higher in energy than the atomic orbitals. The orbitals are formed between the atoms, forming the molecular orbitals, and the electrons enter the lowest orbitals available. They fill these orbitals according to the Pauli exclusion principle and Hund's rule. Some simple examples of molecular orbitals here are for diatomic lithium and beryllium. As we see here, we have each lithium, we have 3 electrons. We form bonding and anti-bonding 1 sigma, and then this bonding 2 sigma orbital. Whereas for beryllium, we have a contribution of 4 electrons from each beryllium. So the 8 electrons are going to occupy 4 orbitals. We'll have an overall bond order of 0 because we'll have 2 bonding orbitals and 2 antibonding orbitals. And we see that the antibonding orbitals are higher energy than the atomic orbitals, whereas the bonding orbitals are lower energy. Molecular orbitals can get more complex than that. And here's an example of some more diatomics as we go to boron, carbon, all the way up to fluorine. We see that we start to divide orbitals into either sigma or pi, even delta bonds, which none are pictured here. We also have terms to describe them, gerada and ungerada. And as we see that there are some orbitals where the energies of the orbitals are degenerate. So there's certain orbitals that have the same energies. And what we want to point out here is as we're filling these orbitals, we do see a shift from lithium to nitrogen. The orders go sigma, pi, and then another sigma. Whereas for oxygen and fluorine, we have the sigma, 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 and pi. So depending upon the orbitals, the energy relationship between the orbitals, how those electrons are going to fill those orbitals will differ. And it's one of the things we see for oxygen, for dioxygen, we wind up having 2 unpaired electrons because they wind up going into the 2 pi ungerada orbital, and they each occupy 1 level, so they are not spin paired. So we can see that this difference between not the first 2 orbitals, but once we get to the 3rd and 4th orbital, we get this change from lithium to nitrogen being one set, then oxygen and fluorine being another set, and actually derives some of the properties of oxygen having 2 unpaired electrons. The examples we just discussed were fairly straightforward, being diatomic molecules. Now we'll look at some where we have mixtures of different molecules. So this is bonding between fluorine and hydrogen. We see that we get orbitals where the energies are much closer to the fluorine, some that are exclusively the fluorine, and much lower energy for the hydrogen bonding. We don't get, and the reason we have these non-bonding orbitals here is that the hydrogen does not have any pi orbitals that it can contribute to the bonding, so there's no overlap. And these non-bonding orbitals are going to have energy characteristics very similar to the p orbitals in hydrogen. More complex views of these molecular orbitals can be found for something called symmetry-adapted linear combinations of orbitals. These where we look at the atomic orbitals and we match out the molecular orbitals by having the best overlap between the atomic orbitals. And this is for carbon dioxide. We see that there are a number of orbital states where we have lower energies or some non-bonding where the characteristics are either the oxygens, such as some of these 2p oxygens. And we see that some of the energy differences between the bonding and the anti-bonding orbitals can be pretty large. The crystal field theory is particularly useful to describe changes in the degenerate states of metal ligand complexes, and these changes stem from interactions of the d and f electrons. Within the crystal field theory, the lone pair of these f or d or f electrons are modeled as points. So electrons can be repelled in these orbitals, and that winds up splitting those fields. For instance, in d orbitals, have energy differences due to the lone pair being modeled as a point. This results in ligand field splitting, and for the case of d orbitals, these can be from going from a spherical to an octahedral environment. The d orbitals are split into t and e orbitals. Now this ignores a covalent contribution, which can be fit later. This energy difference, this delta term, this is called the ligand field splitting parameter, and this can be determined by absorption spectroscopy, where we have a transition from this T2G to the EG. We measure that through UV visible spectroscopy. An example of that measurement is provided here for titanium aquo species, where we see the absorbance, and it's measured here in wavelength and in here in wave numbers. We can use this to determine the ligand field splitting parameter, and it's found that the splitting parameter varies with the ligand. We already know that we can use UV vis spectroscopy to determine the speciation, but that change in the wavelength can also be used to determine changes in the molecular orbital of the complex. For metal ion, increases with oxidation state, the ligand field parameter increases with oxidation state and increases down a group. There are some trends that are observed from changes of the ligand, and here are some ligand field splitting parameters for some metal L6 complexes where we have different ligands and different metal ions filling from D3 to D8 electrons. The ligand field stabilization energy can actually be evaluated from this field parameter, and we see that the T2G stabilizes the field where the EG increases the field. So we see that the T2Gs for the octahedral system tends to be the binding orbitals, where the EGs can be the non-bonding orbitals. And then here's some stabilization energies that are given for different metal ions from D0 to D10 for both the octahedral and the tetrahedral fields, for both strong and weak fields, and we'll describe these strong and weak field terms. The strong and weak fields can really be best examined by evaluating the location of the fourth d electron. So if we look at a D4 system, we can fill the orbitals two ways. These are our T2G, here are our EG orbitals. We can either put all four electrons in the T2G, or if the energy difference from the T2G to the EG is relatively small, I can put 3 electrons in the T2G and 1 in the EG. These are described as weak fields, and the weak field, I'm going to have all the electrons, all 4 electrons unpaired. So this is going to be a high spin. So the weak field is also called a high spin system. And why is it called high spin? Well, all these spins add up. They're all in the same direction, all parallel. So I have a higher spin on this complex. If it's a strong field, all that means is that the energy gap between the T2G and the EG is large enough, so I can't promote this unpaired electron to the EG. It's got to form a pair with the T2G. That means it forms a anti-parallel pair, and there's 2 unpaired electrons. So this is a low spin situation. So we can either describe this splitting as either strong field or weak field, or low spin and high spin. Generally, the 4D and 5D have this ligand field splitting parameter greater than the 3D. So we're going to see that they're going to generally have low spin. Magnetic properties can also be used to evaluate the splitting parameter, since the pairing of electrons are going to influence the magnetic behavior of the complex. Some of the terms that are used are diamagnetic or paramagnetic, and fundamentally for this effort, what one would do is evaluate magnetic moments, and one could calculate and compare to experiment. This would give ideas whether or not those electrons are paired or unpaired. Now, the crystal field theory, as we already described, is for octahedral. It can also split differently for tetrahedral environment. As we see in the octahedral, the lower energy was the T2G, the higher was the EG. In the tetrahedral environment, this is reversed. And we can even go from octahedral to tetragonal environment, where we basically elongate one of the axes. We wind up splitting both the T2G and the EG. A final method for describing metal-ligand interactions is the ligand field theory. And fundamentally, the ligand field theory is really the application of the molecular orbital theory for transition metals. This describes bonding and geometry for coordination complexes. This includes covalent metal-ligand interactions, and is particularly useful for describing overlap of ligand with metal orbitals. An example of the ligand field theory for d orbital hybridization is listed here. For a complex of phosphorus and chlorine, we see that we have 1, 2, 3, 4, 5 chlorine bonds. All these bonds need to be at least the same energies, the same distances. So we know that we need to mix our orbitals together. So we come up with a hybridized orbital. In this case, we have 5 sp3d orbitals, which are all the same, so that this complex will have similar phosphorus-chlorine bonds. This can be expanded for the ligand field theory. This is an expansion of the molecular orbital theory, where in this case for the metal ligand overlaps, we have 6 bonding electrons. We know these are bonding because their energies are lower than both the metal and the ligand orbitals. There are also 6 non-bonding electrons. We see that all these orbital energies are higher than the metal and the ligand orbitals. And we have 3 non-bonding orbitals, and we see that these non-bonding orbitals come from the 3d metal orbitals, so we would expect these to have metal characteristics. And here, the promotion from this highest occupied molecular orbital to lowest unoccupied molecular orbital will give us our ligand field splitting parameter. So UV-vis spectroscopy will measure the energy from this orbital to this antibonding orbital. So the ligand field theory describes how s, p, d's, and f orbitals on the metals can overlap with orbitals on the ligand to form molecular orbitals. An example of the symmetry-adapted linear combinations for some metal and ligand interactions are presented here. And what this shows are the molecular orbitals that are formed from the atomic orbitals of the metals and the ligands and how they would split from the metals forming this Eg T2G, which ligand orbitals and which metal orbitals overlap to form the bonds. And here's a detail of a molecular orbital that's described from this ligand field theory, where we have sigma and Eg T2G orbitals, and along with the crystal field splitting parameters, and whether or not these are bonding, non-bonding, or anti-bonding orbitals. Charge transfer bands can also be observed in the UV visible spectra. These tend to have very large molar absorptivities, so they can be dominant peaks. And the charge transfer bands can be divided into two. You can have a ligand to metal charge transfer band. An example here are electrons, which are ligand in nature, being promoted to an orbital which is primarily metallic in nature, so we have a ligand to metal charge transfer band. The other route would be metal to ligand, and this is shown here, where we have these T2Gs going to ligand orbitals in UV visible spectra. These energies are relatively high, so we'd expect these molar absorptivities to be observed at lower wavelengths. Now, an example for this with the actinides is shown here for the uranyl complex, UO2 2+. One of the interesting properties of the eel molecules for the actinides is the linear behavior of the oxygen actinide oxygen system. And this behavior stems from the interaction of the F electrons in the formation of the molecular orbital. So from the molecular orbital, we see that the metals, the uranium, contributes Fs and Ds, where the oxygens are going to just contribute S's and P's. We see that the highest occupied molecular orbital is a mixture of sigma and pi bonds, and what we measure in UV vis is this transition. Okay. What we went over should describe bonding and structural relationships. One should be able to understand how coordination number is related to geometry, how the geometry is related to point groups, how we get those point groups, and a few routes on how we can describe metal-ligand interactions, some from acid-base reactions, where we describe them as soft or hard interactions, and then the models, where we described molecular orbital theory, charge transfer reactions or crystal field theory, and ligand field theory, which is the application of molecular orbital theory to metal-ligand interactions. Questions that would be related to what we discussed are listed here. Which ligands would you expect to bind strongly with either iron or mercury? Soft mercury, harder iron. Describe the chelate effect. What does IR and UV vis spectroscopy inform about a chemical species? Please provide some comments on this lecture using the blog and respond to the PDF quiz number 4.